All right, so good morning again, everyone. My name is Vincent. I'm IVM Technologies co-founder and CEO. So today I wanted to share with you some case studies and feedback from previous operations applied to offshore wind farms, especially what computer vision can bring to it, more specifically photogrammetry. So I'll give you a quick presentation of our company and share with you some feedback from recent operations. So at IVM Technologies, what we offer, what we bring as a solution to the market is 3D modeling solutions that are primarily aimed at optimizing subsea asset inspection. And by optimizing, we mainly mean saving operational time, saving vessel time. And to do so, we use a technology called stereo photogrammetry. And by saving time, compared to what? Compared to existing technologies such as acoustics or LIDAR, for example. So a little bit more about IVM. We created this company end of 2020, just after the first lockdown. And primarily, we were existing as the innovation department of Comex. The old French Comex company started in the early 60s. So we were their innovation department, and that's where we developed this technology. But back then, we were a service providing company. So we were working with, let's say, very good prototypes, advanced prototypes. And we did service for about 4 years. And with the COVID crisis, Comex decided to went in certain direction, but there was a real market for this technology, and it was mature enough to bring it to the market as a product. So when we started IVM Technology, we moved from being a service provider to being a technology provider. So now we offer our products, this technology as a product. We're a team of about 15 people in the south of France, and we work in many different markets, not only renewables, but also oil and gas, civil engineering, nuclear power plants, defense, and biology, subsea science. So a lot of you know about photogrammetry, but what is photogrammetry and how is computer vision applied to subsea inspection? Photogrammetry, in one sentence, is about being able to build a 3D model of a subject based on 2D images. So we take a bunch of pictures of a subject from different positions, and then we look for common points between these pictures, align them together, and we bring out a point cloud. From this point cloud, we can create a mesh, we can apply the texture, and it can be very, very accurate. So again, we're back to the differentiation from acoustics and LIDAR. First of all, the accuracy and the rendering as well is quite unique and quite different. Also, this technology can be so accurate that you can have it endorsed, certified, supported by classification societies such as Bureau Veritas. So for mandatory inspections, insurance subjects, this technology is not only claimed accurate, but demonstrated to be accurate. For those of you who know photogrammetry from the past, because it's a fairly old technology, you remember about computer vision requiring a lot of post-processing. So it would take a lot of time to acquire data, and then you would have to spend days and weeks and sometimes months to process it. Today, I don't know if I can move that quicker, but today, we're able to do that processing in real time, meaning that as you take your data, you have a 3D model that can be built as you do your survey. Messieurs, est-ce qu'il est possible d'avancer un tout petit peu la vidéo avec ça ou pas? Merci. So, for instance, here, this is not a final post-processed 3D model, but you can already see what the subject looks like, and that's in real time. And even if you're not getting your final accuracy, you can see what the subject is supposed to feel like, how much progress you've made, how far you've been in your survey, and more importantly, have you missed something? Is everything in the box? Can we tell the offshore boss, yes, everything is done, we can go back? So at the moment, the use of SLAM in subsea inspection is more towards quality control, survey assistance, but in the near future, it will be final processing in real time. For now, this is an assistance during the survey, and you still need to post-process, but you minimize the risk of having to come back. So again, we are back to optimizing survey, optimizing subsea inspections, and by minimizing the risk of having to come back on site. This computer vision technology is very good because you can integrate it on all vehicle sizes, from tiny mini ROVs like the Blue ROVs, the Video Rays, Subsea Tech, who's over there, many different ROV makes, and you don't need very large vehicles, and I'll be talking about that again later. So, enough about IVM. What I wanted to discuss with you today is a challenge that offshore wind farms will be facing but should be accounted for today. We're discussing a lot about how this energy will be renewable, profitable, and how we can create solutions, bring solutions that will apply to the offshore world. Very often, the inspection side, the O&M, operation and maintenance, is too little regarded. And however, it presents a few challenges. So, first of all, the volume of inspections on a wind farm, you have many different assets, similar assets that you need to inspect all at the same time, whether it's fixed wind farms, with the piles, the cables, or if it's floating with all the moorings. On an oil and gas field, if you have an FPSO, yes, you have the mooring lines. On a floating wind farm, you have a lot more of mooring lines to be inspected. But it's the same importance for the reliability of the asset. Also, the type of resource that we are using for subsea asset inspection in offshore wind farms. Today, it's very often we hear that the offshore wind farms will be or are inspected with the same type of assets, capabilities as of the oil and gas. So, in the oil and gas, it's not a problem if you have a 120-meter long vessel with 50 to 80 people on board, because it will be profitable in the end. If you have such a vessel for every turbine that is going to be there 6 months for all the mooring lines or all the piles or all the cables, the price, the cost of your electricity is going to go up. So making offshore wind farms possible and profitable is not only about how we build them, but it's also about how we inspect them. So some of the ways, some of the tracks that we have are, of course, about reducing vehicle size, because, as I said, work boats, inspection boats from the oil and gas industry are very large, and either you reduce the amount of inspection you have to do, or you minimize the size, or you can do both. But also you need to maximize doing remote control or bring autonomy on this vehicle. And that's how we will mainly reduce the costs of this inspection. And in addition to that, you can also bring technologies that are not widely used yet. Some things that are innovative and that will make a difference, will bring more value to the inspection of the wind farms. So let's take a few use cases, case studies that are real case studies on which IVM worked. So these are from the oil and gas, but platform jacket inspection, spool metrologies, for you who know what that is, between a well and a pipeline termination. That's time is of the essence in these. And mooring lines. This is the same case. So on a jacket inspection, an area that is 10 by 10 by 10, let's say, this inspection done by divers or by LiDAR was taking between 12 and 48 hours. It used to take between 12 and 48 hours. The same done with photogrammetry means that you just get into the water, grab the data, and you don't carry any inspection on site. You build the 3D model back in the office, and you carry your analysis, your actual inspection from the office, because the model is accurate enough, is detailed enough, has enough features, so that you don't need to stay on site. So you don't have a massive boat with 50 people hanging around while the inspector is wondering whether the weld is okay. You will do that in the office where it's cheap, where your carbon footprint will be minimum. So on this scope in the North Sea, on pretty old platform decommissioning projects, compared to previous jobs that were done by LiDAR, we were saving 10 hours per area. And there were 10 areas to be inspected. 100 vessel hours saved on a single project. Do you know how much a vessel costs per day for inspection? Between, let's say, 50 and 200 a day, depending on the spread and the amount of people. Between 50 and $200,000 a day. So 100 vessel hours is massive, and that's how you reduce the cost of your energy. Spool metrologies. Spool metrologies is about building the last piece of pipe that is connecting a wellhead and the pipeline. And it has to be done quick, and it has to be done accurately because you don't want to build it multiple times. Today, this is mainly done by acoustic solutions or taut wire. This was a project in the Caspian Sea where it was supposed to be done by divers, so a shift and a half, 18 hours. And if it had to be done, if it had been done by the acoustic methodology, LBL array, it would have taken around a day and a half. With a photogrammetry system that doesn't require navigation aid, that doesn't require referentials, no markers, no scale bars, we spent 3 hours in the water, 3 hours. And we did 2 of them, and they were pretty large, 52 meters and 64 meters. So the amount of vessel saving, again, is enormous, between 15 to 30 hours per spool metrologies. So I'm still on the oil and gas, I know. I will transit to the offshore wind farms after. Mooring lines. So this is an FPSO, but again, we can say it's a floating turbine. Today, the inspection of the mooring lines, it's primarily done with, these giant calipers that the ROV has to hold and bring onto the chain and grab the chain to take a few measurements. And it has to do that on multiple links, multiple times, with the vessel standing by. Now imagine doing this with swell, current, a tired ROV pilot who has not slept well. So for a chain strip of 5 links, taking these measurements can take between 1 to 6 hours. let's say 2 hours on an average. With computer vision, you don't have to touch the chain, just fly randomly around it. And you will use maximum half an hour, maximum 30 minutes. And again, you won't be taking your measurements or carrying any inspection on site with the vessel and the personnel standing by. You will bring the inspection back to shore where it's cheap and cost effective and where the carbon footprint is very low. Again, big vessel time saving. Now, let's say we transpose these case studies to wind farms, wind turbines, inspections of piles and cables. Everybody knows about the cable protection system issues that we have all over the world, all across the world. Well, to inspect these cable protection system by divers or taking measurements with an ROV, it takes hours and days. Here, in 2 hours, less than 2 hours, you can inspect a cable protection system in the North Sea in bad visibility, again, without touching anything, and carry on the inspection in the office. Pile metrology. It's the same as spool metrology. You have to accurately position them, and today it's being done with acoustic. And again, computer vision can bring an alternative to this that will save massive operational time. And mooring lines, it's the same for floating assets. And there are many other case studies. Damage inspection, corrosion, but also fouling follow-up, what we call biofouling, which is fouling, but follow-up of fouling over the years and building a digital twin that you will overlap every year to see how one has grown or disappeared. So in the end, again, how can we contribute to minimizing the cost of energy in offshore renewable energies? There is also the aspect of autonomous navigation, as I said earlier. Today, AUVs are very capable of flying from long distances of a subject. So they fly in the blue very well. As soon as you need to get closer than 5 meters to a subject, well, it gets tricky because acoustic is not accurate enough because the inertial system derivates too much. Well, guess what? Below 5 meters, you see pretty well, even in bad visibility. So there again, computer vision is an added layer that we need to integrate, we need to hybrid, and which we are working on, to extend the capabilities of subsea autonomous navigation. And what IVM Technologies is working on for the future, apart from the sensors that we are providing to the market today, is using the IVM SLAM to provide a position, an orientation, a speed, an acceleration, and that is autonomous underwater navigation. So a bit more details about this video that we saw on extract earlier, but as you're doing your survey, you're taking pictures of your subject, and you know in real time your position, your orientation, and your location in the mapping that you have already produced from close distances to your subject, which acoustic, LIDAR, and inertial cannot provide to this day. So we don't, computer vision will not replace these technologies, but it will come as a complement in the near future. All right, that's it for me. Thank you for your attention and for being here today so early.